Hello and welcome to NEET Prep Go. So let's revise. So we are doing S block elements. We learned about that is S block elements consist of group 1 and group 2 elements which are respectively known as alkali metals and alkaline earth metals. They both have NS1 and NS2 configuration because that is they are called as S block elements because the last electron enters the S orbital. The first elements, that is lithium, beryllium, they both show anomalous behavior. Alkali metals because they react with water to form hydroxides which are strongly alkaline in nature. Alkaline earth metals because their oxides and hydroxides are alkaline, plus they are found in Earth's crust. Then exception is beryllium when it comes to alkaline earth metals. Then sodium, potassium among the alkali metals are most abundant. Lithium, rubidium and cesium have lower abundance, but francium 223 that is has a half-life of only 21 minutes. Then alkaline earth metal, calcium and magnesium have higher abundances, whereas beryllium is very rare and radium is even rare, only 10 to the power 10 of the igneous percent of the igneous rocks. And strontium and barium have lower abundances. NS1, NS2 you know already. Diagonal relationship, that is both lithium and beryllium show anomalous behavior, so they are not similar to the members of their own group, but lithium is similar to magnesium, which is an alkaline earth metal, and in the following period of lithium. And similarly beryllium is diagonally, that is similar to aluminium. So this is called as diagonal relationship because their properties are diagonally similar to the elements. That is, you can see the diagonal relationship. It is based on similarity in ionic sizes, charge, radius, ratio and all. Then that is monovalent ion, sodium, potassium and divalent ion, magnesium, calcium, they are found in large portions in biological fluids, and they perform biological functions such as maintenance of ion balance and impulse conduction. Then we know that first alkali metals, that is they lose their only one loosely bound valence electron readily, and therefore they are never found in free state in nature. Ionic radii, that is as we go down the group the ionic radius increases, that is M plus, when they lose M plus is smaller in size than the neutral atom. Then ionization enthalpy, that is ionization enthalpy is considerably low and it decreases down the group because new shells start getting added, nuclear charge increases, but not as compared to the ionic that is the radius and outer shells getting added. So therefore shielding or screening takes place, and the outermost electron becomes more and more less attracted towards the nucleus, and hence easier to remove as we go down the group. Then hydration enthalpy, with the increase in ionic size, hydration enthalpy decreases. So lithium has the highest hydration enthalpy. It is also smallest in size. Then most lithium salts are hydrated. Example LiCl2F.2H2O. Then all alkali metals are either silvery white, soft, light metals because of their large size and they have very low density, and the density increases from lithium to cesium. The only exception is sodium, which is has a higher density than potassium, or potassium has lighter density than sodium. Then melting and boiling points are also low, and melting and boiling points also decrease as we go down the group. Then alkali metals and their salts impart characteristic color: lithium, that is crimson red, sodium yellow, potassium violet, rubidium red violet, cesium blue. Alkali metals can therefore be detected by the responsive flame test, that is flame photometry or atomic absorption spectroscopy. Light energy absorbed may be sufficient to make an atom lose electron. Then we read all the trends of physical properties. After this we come to chemical properties, and the property of like that is the property of light energy absorbing, and that is enough energy absorption to lose an electron is used by potassium and cesium, useful as electrodes in photoelectric cells. Now chemical properties. Chemical properties: reactivity towards air. They tarnish in dry air due to formation of their oxides, which in turn react with moisture to form hydroxides. They burn vigorously in oxygen. So therefore, you can see that lithium forms oxide, whereas sodium forms peroxide, and potassium, rubidium, cesium forms superoxide. And in all of these, the oxidation state of alkali metals is going to be +1. Now reactivity towards water. The alkali metals react with water to form hydroxide and dihydrogen H2. It may be noted that lithium has the most negative E0 value, and even still its reaction with water is less vigorous than that of sodium, which has the least E0 value. So this behavior is basically, again, for lithium it is anomalous only, and this is basically due to very small size of lithium and very high hydration enthalpy, hydration energy of lithium. Other metals in the group react explosively with water, and they also react with proton donors such as alkynes, alcohol, and gaseous ammonia. Now reactivity towards dihydrogen, that is all the alkali metals at 673 Kelvin and lithium exception at 1073 Kelvin form hydrides, and all the alkali metal hydrides are ionic solids with very high melting points. Then reactivity towards halogen, the alkali metal readily react vigorously with halogens to form ionic halides M plus X minus. The alkali metals readily react vigorously with halogens to form ionic halides N plus X minus. However, lithium halides are somewhat covalent. It is because of the high polarization capability of lithium ion. Reactivity towards halogen. The alkali metals readily react vigorously with halogens to form ionic halides. So reactivity towards halogen, that is the alkali metals readily react vigorously with halogens to form ionic halides. So now we saw reactivity towards air, that is in air lithium was forming oxide, sodium was forming hyperoxide, and potassium, rubidium, cesium were forming superoxide. Then we saw reaction towards water, that is all of them were forming hydroxide and dihydrogen. Then we saw reaction towards dihydrogen only, and we saw that all the metals were giving that is metal hydrides. Now reactivity towards halogens. The alkali metals readily react vigorously with halogens to form ionic halides, that is M plus X minus. So this was M plus H minus, that is alkali hydride. Now ionic halides are formed, and however lithium halide are somewhat covalent. So, reactivity towards hydrogen, alkali metals readily react with halogen to form ionic halides. However, lithium halide is somewhat covalent. Why? This is because of the high polarization capability of lithium ion. So, what is polarization? That is the distortion of electron cloud of the anion by the cation is called as polarization. So, high polarization capability of lithium ion. The lithium ion is very small in size and has high tendency to distort the electron cloud around the negative halide ion, and since an ion with large size can easily be distorted among halides, lithium iodide is most covalent in nature. This is very important line. Lithium halide. So basically due to lithium's small size, and obviously the anion will be of very large size, let's say chlorine, bromine. So So lithium, basically the electron cloud, that is lithium cation, basically when changes the that is, or distorts the anion, that is the electron cloud of the anion, then it is called as polarization. That is and due to the very high tendency and small size, that is of the Li ion, it's, even though all the alkali metals form ionic halides, lithium on the other hand forms one of the most covalent, that is lithium forms mostly like somewhat covalent, lithium halides are somewhat covalent, and the most covalent in nature, that is among halides, is lithium iodide. Lithium iodide is most covalent in nature. Lithium iodide is most covalent in nature. Hmm. Now reducing nature. Reducing nature. The alkali metals are very strong reducing agents. The alkali metals are very strong reducing agent. Lithium being the most and sodium being the least powerful. So among reducing agents, lithium is the most reducing agent and sodium is the least reducing agent. The least powerful reducing agent. The standard electrode potential E0, which measures the reducing power, represents the overall change. Sublimation enthalpy, ionization enthalpy, hydration enthalpy. So that is, solid to gas is called as sublimation, directly from solid to gas. And sublimation enthalpy, how easily it is getting sublimated. Ionization enthalpy, how easily with the help of energy the element is giving up electrons. And hydration enthalpy, that is readily dissociating in water, reacting with water. With small size of its ion, lithium has the highest hydration enthalpy, which accounts for its high E0 value and high reducing power. So how you can justify that lithium has the highest reducing power? It is because of its highest hydration enthalpy, lower size, and high E0 value. Therefore, it has high reducing power. For the E0 for Cl2 or Cl minus is plus 1.36. For I2 it is plus 0.53, and for Ag plus it is 0.79. Na it is minus 2.71, lithium it is minus 3.04. Arrange the following ionic species in decreasing order of reducing strength. So it is always going to be lithium, that is according to this, lithium, then sodium, then iodine, then Ag, and then Cl. See, this is minus 3.04. Now solutions in liquid ammonia. The alkali metals dissolve in liquid ammonia, giving deep blue solutions which are conducting in nature. Solutions in liquid ammonia. The alkali metals dissolve in liquid ammonia, giving deep blue solutions which are conducting in nature. So this is M in X plus Y NH3, M NH3X, and E NH3Y. The blue color of the solution is due to ammoniated electron, which absorbs energy in the visible region of light and thus imparts blue color to the solution. The solutions are paramagnetic and on standing slowly liberate hydrogen, resulting in the formation of amide. So what happens to solutions in liquid ammonia? That is, the alkali metals dissolve in liquid ammonia and they give deep blue solutions which are conducting in nature. In liquid ammonia, the alkali metals give deep blue solution and these deep blue solutions are conducting in nature. So M in plus X plus Y NH3, that is liquid ammonia, gives MNH3X and ENH3Y, that is the blue color of the solution is due to ammoniated electron which absorbs energy in the visible region of light. So the blue color in the solution is due to the ammoniated electron, and this ammoniated electron absorbs energy in the visible region of light and thus imparts blue color to the solution. Hence and therefore it imparts blue color to the solution. The solutions are paramagnetic. So in coordination compound you must have learned about paramagnetic and diamagnetic. That is when there are in the that is when there are the unpaired electrons, that is then in the orbital, then it is those can get excited and they can show color, that is paramagnetic behavior. Diamagnetic, that is paired. So that is all electrons are paired in the orbital, so freely can't move, diamagnetic. On standing slowly, this solution, that is this deep blue solution which became blue in color due to ammoniated electron which absorbed visible region, that is energy in the visible region of light and gave blue color to the solution. These solutions are paramagnetic and on standing slowly they liberate hydrogen, resulting in the formation of amide. Arm node solution in ammonia. So this AM node solution in ammonia. In concentrated solution, the blue color changes to bronze color and becomes diamagnetic. So in a concentrated solution, this blue color changes to bronze color and it becomes diamagnetic. Now we come to uses. Lithium metal is used to make useful alloys, for example with lead to make white metal bearings for motor engines, with aluminium to make aircraft parts, and with magnesium to make armor plates. Lithium is used to make useful alloys, with lead it is used to make white metal bearings for motor engines, with aluminium it is used to make aircraft parts, with magnesium to make armor. Wait, let me use highlighter. Lithium metal is used to make useful alloys, for example with lead to make white metal bearings for motor engines, with aluminium to make aircraft parts. What happened? Oh, anyways, that's good. Lithium is used to make useful alloys, for example with lead lithium is used to make useful alloys, for example with lead to make white metal bearings for motor engines, with aluminium it is used to make aircraft parts, and with magnesium it is used to make armor plates. So lithium firstly it makes useful alloys. Lithium makes useful alloys. Then with lead it makes white metal, which white metal bearings for motor engines, with aluminium aircraft parts, and with magnesium armor plates. Okay, so armor, one that the plates, armor is what kings and all used to wear. So it is used in thermonuclear reactions. Lithium is also used to make electrochemical cells. So till here it is lithium. It's very important. So there are so many. First use, lithium is used to make useful alloys. Then secondly, it is used to make white metal, that is with lead. It is used to make white metal bearings, white metal, that is bearings for motor engines. Then with aluminium it makes aircraft parts, that is with aluminium it makes aircraft parts. Then with magnesium, that is with magnesium armor plates. Then with that is, it is also used in thermonuclear reactions, and also it is used to make electrochemical cells. It is used to make electrochemical cells. Okay, so lithium is used to make useful alloys, white metal bearings for motor engine, aluminium, that is with lead to make white metal bearings for motor engines, with aluminium to make aircraft parts, with magnesium to make armor plates, and it is used in thermonuclear reaction. It is also used to make electrochemical cells. Sodium is used to make sodium lead alloy needed to make PbEt4 and PbMe4. The organo-lead compounds were earlier used as anti-knock additives to petrol, but nowadays vehicles use lead-free petrol. Liquid sodium metal is used as a coolant in fast breeder nuclear reactors. So all of these things you have to learn. There's no way to escape. Potassium has a vital role in biological systems. Potassium chloride is used as a fertilizer. Potassium hydroxide is used in the manufacture of soft soap. It can also be used as an excellent absorbent of carbon dioxide. Cesium is used in devising photoelectric cells. Okay. So first we remember that lithium is used to make useful alloys. Secondly, lithium when combined with lead makes white metal bearings for motor engines. Then that is lithium with aluminium is used to make aircraft parts. Then lithium is also used in thermonuclear reactions and thermonuclear reactions, and it is also used to make electrochemical cells. Then it is also used to make a sodium lead that is okay, and it is also used in electrochemical cells. Okay, that is with lithium. Now sodium is used to make sodium lead alloy and needed to make lead DET4 and Me4. These organo-lead compounds were earlier used as anti-knock additives to petrol, but nowadays lead-free petrol is being. So earlier these were used. That is sodium lead alloy. That is sodium was used to make sodium lead alloy, and this alloy was needed to make PbEt4 and PbMe4, and these were the organo-lead compounds which were used as anti-knock additives to petrol. But now lead-free petrol is being used. Okay, so now liquid sodium metal is also that is liquid sodium metal is used as a coolant in fast breeder nuclear reactors. That is liquid sodium metal is used as a coolant in fast breeder nuclear reactors. Potassium has a vital role in biological systems. We know in bio also we will study that potassium chloride is used as a fertilizer. Potassium hydroxide is used in the manufacture of soft soap. Okay, so this is also very important. Potassium has a vital role in biological systems. How? That is, potassium is used as a, that is potassium chloride, potassium KCl. Potassium chloride is used as fertilizer. Then potassium is used in the manufacture of soft soap. Then it is used as an excellent absorbent on carbon dioxide, and cesium is used in devising photoelectric effect. Cesium is used in devising photoelectric effect. Excellent absorbent on carbon dioxide. Okay, now let's come to general characteristic of the compounds of the alkali metals. So what are the general characteristic of the compounds of the alkali metal? That is, all the common compounds of the alkali metals are generally ionic in nature. General characteristics of some of their compounds are discussed here. What are the general characteristics? That is, they are all generally ionic in nature, and general characteristics of alkali metal, that is group 1 elements, are discussed over here. Oxides and hydroxides. On combustion in excess of air, lithium forms mainly oxide. We read above, that is on reaction with air, that is excess air combustion, lithium forms Li2O plus some peroxide Li2O2. Sodium forms peroxide Na2O2 and some superoxide NaO2, whilst potassium, rubidium and cesium only form superoxides MO2. Under appropriate condition, pure compounds M2O, I should, it's not visible, right? On combustion in excess air, on combustion in excess air, that is lithium forms mainly oxide Li2O that we read above, but it also forms some peroxide Li2O2. Then sodium forms peroxide Na2O2, but it also forms some superoxide NaO2. Then whilst potassium, rubidium and cesium, they all only form superoxide, that is MO2. Under appropriate condition, pure compounds M2O oxide, that is MO2 uh, peroxide and M2O2 peroxide and MO2 superoxide may be prepared under appropriate conditions. The increasing stability of the peroxide or superoxide as the size of the metal ion increases is due to stabilization of large anions by larger cations through lattice energy effects. These oxides are easily hydrolyzed by water to form hydroxides according to the following reactions. Okay, so on combustion in excess air, lithium forms mainly oxide Li2O that we already read, plus it forms some peroxide, that is Li2O2. Then sodium forms peroxide Na2O2 plus some superoxide NaO2. Then whereas potassium, rubidium and cesium, all of them form superoxides MO2. Under appropriate conditions, pure compounds such as M2O, M2O2 and MO2 may be prepared. The increasing stability of peroxide or superoxide, that is, the increasing stability of peroxide or superoxide as the size of the metal ion increases is due to the stabilization of larger anions by larger cations. So we know that lithium was like very small in size, so it is, the cation is very small as compared to the anion, but as the ionic size increases, the stability of peroxide as well as superoxide increases. This is because the size of metal ion increases, and it is the stabilization of large ions takes place by cations which are also large through lattice energy effects. So through lattice energy effects, the stabilization of larger cations takes place by large anions takes place by larger cations. These oxides are easily hydrolyzed by water to form hydroxides according to the following reaction. So M2O plus H2O gives 2M plus 2OH minus. M2, that is peroxide, plus water gives 2M plus OH minus plus H2O2 peroxide. MO2 plus 2H2O gives okay. Now M2O2 plus 2H2O plus 2M plus 2OH minus and H2O2. Now 2, why is this happening? The oxides and peroxides are colorless. Okay, so 2MO2 plus 2H2 is 2MOH, H2O2 plus O2. Okay. The oxides and peroxides are colorless when pure, but बापरे, small, then let's see half. तो कुछ भी हो रहा है. So the oxides and peroxides are colorless when pure. So basically there's no color in oxides and peroxides when they are pure, but the superoxides are yellow or orange in color. The superoxides are either yellow in color or orange in color. Superoxides are either yellow in color or orange in color, and the superoxides are also paramagnetic. Therefore, they are showing color, right? Paramagnetic, that is unpaired electrons, they will get excited, and if they get radiated, that is in the visible region, then they will start showing color. So, superoxides are paramagnetic. So, superoxides are yellow or orange in color, whereas oxides and peroxides are colorless when they are pure. Now, sodium peroxide is widely used as an oxidizing agent in inorganic chemistry. That is, sodium peroxide, Na2O2, is used uh, widely as an in oxidizing agent in inorganic chemistry. Why KO2 is paramagnetic? That is, the superoxide O2 is paramagnetic because of unpaired electrons. The superoxide O2 because of unpaired electrons in pi star 2p molecular orbital. So whoever has studied chemical bonding properly, you know that paramagnetic because unpaired electrons are in pi star 2p orbital. Now, hydroxides. The hydroxides which are obtained by the reaction of the oxides with water are all white crystalline solid. The alkali metal hydroxides are the strongest of all bases and dissolve freely in water with evolution of much heat on account of intense hydration. So hydroxides which are obtained by the reaction of oxides with water are all white crystalline solids. The alkali metal hydroxides are the strongest of all bases. They are the strongest of all bases and they dissolve freely in water with evolution of much heat on account of intense hydration. So the alkali metal hydroxides are strongest of all bases. So firstly, the hydroxide metal bases which are hydroxides which are obtained by the reaction of oxides with water are all white crystalline solids, and the alkali metal hydroxides are the strongest of all bases and they dissolve freely in water with evolution of much heat on account of intense hydration. Due to intense hydration, there is much evolution of much heat. Then halides. The alkali metal halides, Mx, that is X can be fluorine, chlorine, bromine, iodine, they are all high melting, colorless crystalline solids. They can be prepared by the reaction of the appropriate, again it happened. They can be prepared by the reaction of the appropriate oxide, hydroxide or carbonate with aqueous hydrohalic acid. All of these halides have high negative enthalpies of formation. That is delta HF values for fluorides become less negative as we go down the group, while reverse is true for fluoride, bromide, iodide for given metal. It always becomes negative. Okay, we'll have to read again. The alkali metal halides Mx, whether X be fluorine, chlorine, bromine or iodine, are all high melting, colorless crystalline solids and they can be prepared by the reaction of the appropriate oxide, hydroxide or carbonate with aqueous hydrohalic acid. So these halides can be prepared by the reaction of appropriate oxide, hydroxide or carbonate with aqueous hydrohalic acid, that is HX, hydrohalic acid. And all of these halides have high negative enthalpies of formation. Their electron gain enthalpy is very high. So this is something that you must be knowing. So basically, like I said, let's say take sodium, okay, Na plus 1. It is very easy to lose this electron, right? Because the moment with a very little energy we can lose this electron. and this will become noble gas arrangement. So therefore, the ionization enthalpy, or the enthalpy of ionization, wherein you lose one electron, that is how much energy you give. Okay, so that is very less, because इसको तो stable होना है at the end of the day, तो इसीलिए ये आराम से एक दे देगा. But on the other hand, electron gain enthalpy when it comes, then let's say I took chlorine. So we know that the entire group 17, we know group 18 elements are noble gas elements. So group 17, entire group 17 element is one electron less from becoming stable. So they need this negative, that is, they have very high negative enthalpies of formation. Right, the delta HF values for fluoride become less negative as we go down the group, because they need this one electron to get stable, whilst the reverse is true for delta H for fluorides. So all of the halides have high negative enthalpies of formation, and the delta HF values for fluoride become less negative as we go down the group. So I was talking about electron gain enthalpy. This is actually enthalpy of formation, so this is different. Beg your pardon. So the delta F H negative, that is enthalpy of formation values for fluoride, become less negative as we go down the group, whilst the reverse is true for fluorides, bromides and iodides. For a given metal, it always becomes less negative from fluoride to iodide. The melting and boiling points always follow the trend: fluoride greater than chloride, greater than bromide, greater than iodide. Okay, so melting and boiling points, that is, fluoride has the highest melting boiling point, then chloride, then bromide, then iodide. All these halides are soluble in water. The low solubility of LiF in water is due to its high lattice enthalpy, whereas low solubility of cesium iodide is due to smaller hydration enthalpy. Other halides of lithium are soluble in ethanol, acetone, ethyl acetate. LiCl is soluble in pyridine too. Now, salts of oxoacids. Oxoacids are those in which the acidic proton is on a hydroxyl group with an oxo group attached to the same atom. Example: carbonic acid, sulfuric acid, carbonic acid, sulfuric acid. The alkali metals form salts with all the oxoacids. They are generally soluble in water and thermally stable. Their carbonates M2CO3 and in most cases the hydrogen carbonates MHCO3 are also highly stable to heat. As the electropositive character increases down the group, the stability of the carbonates and the hydrogen carbonates increases. Lithium carbonate is not so stable to heat. Lithium, being very small in size, polarizes a large CO3 2- ion, leading to the formation of more stable Li2O and CO2. Its hydrogen carbonate does not exist as a solid. Okay, so let's go up and see once how much we did now. 2 pages. It's a lot of information that I have to remember. Okay, so firstly we saw the activity towards of alkali metals towards water. Okay, so they form OH minus and dihydrogen. And lithium, even though it has the most negative E naught value, still it is less vigorous with water due to its very high hydration enthalpy and small size, whereas others react explosively. And they also react with proton donors such as alkyne, gaseous ammonia and alcohol. Then towards dihydrogen they form alkali, that is metal hydrides, and which are ionic solids with very high melting point, and lithium at 1073 Kelvin react with dihydrogen, whereas all others at 673 Kelvin. Then towards halogens they form mostly ionic halides except for lithium, which forms somewhat covalent halide, and lithium iodide is the most covalent in nature among halides. Why lithium forms somewhat covalent halides? Because lithium has very small size and as a cation, and the large size anion, therefore lithium has the capability to polarize the electron cloud of the anion, and since an ion with large size can easily be distorted, lithium iodide is the most covalent in nature. Now reducing nature. The alkali metals are strong reducing agent, lithium being the strongest and sodium being the least powerful as an reducing agent. The standard electrode potential, which measures the reducing power, represents the overall change, that is sublimation enthalpy, that is from solid to gas, ionization to give electrons energy required, and hydration enthalpy, that is to release M plus ion, that is metal ions in aqueous solution. With small size of its ion, lithium has the highest hydration enthalpy, which accounts for its highest negative E naught value and its high reducing power. So that is the higher the negative value of E naught, that is the more will be its reducing power. So if we see the decreasing order of reducing strength, then lithium having the more highest reducing power is greatest, then sodium, then iodine, then silver, then chlorine. This is according to the values given, E naught values given. Now solutions in liquid ammonia. The alkali metals dissolve in liquid ammonia to give deep blue solutions, and these deep blue solutions are conducting in nature. What are these deep blue solutions? Basically, this is the ammoniated electron which absorbs energy in the visible region and imparts blue color to the solution. It is because the solution is paramagnetic and it standing slowly, it liberates hydrogen, resulting in the formation of amide. The blue color changes to bronze, that is if the solution is concentrated, then the blue color will change to bronze color and become diamagnetic. Uses. Lithium is used. What are the uses of lithium? It is used to make useful alloys. It combines with lead to form white metal bearings for motor engines. With aluminium, it forms the parts of airplane or aircraft parts. With magnesium, it is used to make armor plates. It is used in thermonuclear reaction as well as electrochemical cells. To make electrochemical cells. Lithium. After that, sodium. Sodium combines with lead to form sodium lead alloy, which is used to make PbEt4 and PbMe4. And these organolead compounds were earlier used in anti-knock additives to petrol, but nowadays lead-free petrol is being used. Then liquid sodium metal is used as a coolant in fast breeder nuclear reactors, and that is liquid sodium metal, remember, is used as a coolant in as in fast breeder nuclear reactors. Potassium has many that is vital role in biological system. That is potassium chloride is a very good fertilizer. Then potassium hydroxide is used in the manufacture of soft soap, and it is that is potassium hydroxide is also used as an excellent absorbent of carbon dioxide. So this potassium hydroxide is used in the manufacture of soft soap, as well as it is also used as an excellent absorbent of carbon dioxide. Cesium is used in devising photoelectric cells. Now, general characteristics of the compounds of the alkali metals, that is oxides and hydroxides. On combustion in excess air, lithium forms mainly oxide Li2O plus some peroxide Li2O2. Then sodium forms peroxide Na2O2 plus some superoxide NaO2, and potassium, rubidium, cesium all form superoxides only, MO2. Under appropriate condition, these pure M2O, M2O2 and MO2 may be prepared, and the increasing stability of peroxide or superoxide with the increasing in the size of the metal is due to the stabilization of large anions by larger cations, because as we go down the group, the size increases, that is the atomic ionic radii, it all increases. And this is through lattice energy effects, that is the stabilization of large anions by larger cations through lattice energy effect. These oxides are generally hydrolyzed by water to form hydroxides according to, so these oxides are easily hydrolyzed by water after this to form hydroxides according to the following reactions. and the oxides and peroxides are colorless when they are pure, but the superoxides may be yellow or orange in color. Superoxides are paramagnetic, that is unpaired electron, and sodium peroxide is widely used as an oxidizing agent in inorganic chemistry, which is what is used as an oxidizing agent in widely in inorganic chemistry, that is sodium peroxide. Why is KO2 paramagnetic? Because it has unpaired electron, that is in this pi star 2p molecular orbital, one unpaired electron. Now hydroxides which are obtained by the reaction of oxides with water, these hydroxides, that is with when which are prepared by the reaction of oxide with water, are all white crystalline solids, and the alkali metal hydroxides are the strongest of all bases and dissolve freely in water with evolution of much heat on account of intense hydration. The alkali metal hydroxides, which are strongest of all bases and dissolve freely in water with evolution of much heat on intense hydration. The alkali metal hydroxides are the strongest of all bases and dissolve freely in water with evolution of much heat on account of intense hydration. Then we came to halides. That is, halides are high melting colorless crystalline solid, and they are prepared by the reaction of oxide, hydroxide or carbonate with aqueous hydrohalic acid. That is, halic acid is HX. When the oxides, hydroxides or carbonates of the alkali metals reacts with hydrohalic acid HX, then alkali metal halides are formed, and they all have negative enthalpies of formation. Fluorides, and it becomes less negative as we go down the group. The reverse is for chlorides. Melting point and boiling point, that is of fluoride, is greater than fluoride, greater than bromide, greater than iodide. All these halides are soluble in water, and so this is also very important, that is all these halides formed are soluble in water. Low solubility of lithium fluoride in water is due to its high lattice enthalpy, whereas the low solubility of cesium iodide is due to smaller hydration enthalpy. Other halides are soluble in ethanol, acetone, ethyl acetate. LiCl, lithium chloride, is also soluble in pyridine. Salts of oxoacids. Oxoacids are those in which the acidic proton is on a hydroxyl group with an oxo group attached to the same atom. Oxoacids are those in which the acidic proton is on a hydroxyl group with an oxo group attached to the same atom. Example: carbonic acid, sulfuric acid. We will do oxoacids in the next day. Oxoacids, anomalous properties of lithium. Okay, thank you.